Hello, welcome to a special Christmas edition of I Love Chemistry with Dr. Winchester. Today we're going to look at Unit 2, we're going to look at some redox stuff. And as normal, you've got the video, and just below me you should have a questions little word file and also the mark scheme. So I'm just going to show you how to find this little question that I'm going to get through from a little pack that you should have a go at everyone. Okay? So if we go to the question, it's called REDOX 4 questions. It's not question 1 we're doing, it's lower than that. We're going to do question 2, parts C and D, and then we're going to go on for a little bit of question 3 maybe as well, okay, seeing on time. Okay, so we're doing this one. First of all, we're doing a few oxidation states and then we're making up some equations from the half equations first. Okay, so I'll go back onto the presentation. So the first question is 3 marks, I think, is complete the table below by finding out the oxidation state of each stated elements in the given ion or compound. Okay, so you need to find the oxidation state of an atom. A compound doesn't have an oxidation state, and only one atom will have an oxidation state in a compound. Okay, so the carbon in CO3 2-. So whenever we're working out oxidation states, the first thing to do is think which in my ion or my molecule is the most electronegative. Okay, to do that you look at your periodic table, and the further right and the further up it is, the more electronegative it is. Fluorine is the most electronegative. Anything towards that is getting electronegative, right and up. Okay, so oxygen here is more electronegative than carbon because it's further to the right on the same period. Okay, so oxygen's more electronegative, so it kind of dominates. Now oxygen's in group 6, so it wants to gain 2 electrons to get its full outer shell. Okay, so it wants to gain 2 electrons and be a common O2- ion. Okay, so its oxidation state of oxygen is going to be 2 because it dominates, it gets those electrons, whatever. Okay, so oxygen's oxidation state will be -2. We do Roman numerals, just that's how we do it. Okay, and so we can make sure it's different than the kind of the number that tells you how many atoms there are and the number that tells you the charge. We do Roman numerals because it's an oxidation state. Okay. Now we know there's 3 oxygens, and we know each oxygen has a -2 oxidation state. So we could do a little bit of working, say 3 times -2 equals -6. So overall, all those 3 oxygens needed 6 extra electrons. Okay, but overall the ion is only 2 negative charge, so it only has 2 extra electrons. Okay, so if the overall ion is 2-, but the oxygens have an oxidation state together as an adding up of -6, the carbon must have an oxidation state of +4 to make it be a charge of 2-. Okay, so -6 + 4 equals 2-. So the sum of the oxidation states of all the atoms will always equal the charge. So carbon, if that's +4, plus 1b, if that's +4, 1 times +4 equals 4. 4 take away 6 is -2, so we're right. Okay, so +4 we put in our table, we can write it normal, but that is just when we're having in the formulas that we write like that. Okay, so we're going to quickly rattle through these. Have a go now. So if you didn't know how to do them and you do now, pause it, have a go at these, and then check to see if you're right now. Okay, so let's do phosphorus in PCl4+. So which is more electronegative, phosphorus or chlorine? Well, chlorine is. It's further to the right of the periodic table. It's in group 7. So chlorine's more electronegative. Chlorine wants to gain 1 electron because it's in group 7. So it's going to make one negative oxidation state. So we have the chlorine in -1. So we're asking, what does the phosphorus need to be to make the charge +1? So we have chlorine, we have 4 of them and they're all -1. So -1 times 4 equals -4. We need to make the charge +1, so the phosphorus must be, there's only 1 of them, so it's times the phosphorus must be +5 to give us +5, and when we add them together that gives us +1, which equals that. So you need to make the phosphorus oxidation state +5 to make sure the overall oxidation state of everything equals the charge, which always will. So the phosphorus must be +5 in that example. Don't worry that phosphorus is in group 5, therefore it should want to gain electrons. Okay, chlorine wants to gain the electrons more, so it's gaining electrons and actually made phosphorus lose its electrons. It losing 5 electrons kind of makes sense because it's group 5, so it's lost 5 electrons, almost as if it was a metal. Okay. So let's try this one for magnesium nitrate. Again, which is the most electronegative of magnesium nitrate? It's normally going to be the non-metal, not the metal. But let's prove it to ourselves. Well, magnesium is all the way on the left-hand side here. Nitrogen is both higher up and further to the right, so definitely more electronegative. So nitrogen's going to have its preferred oxidation state. Now, to find out what that is, you need to look at where it is in the periodic table. It's group 5. It wants to gain 1, 2, 3 electrons, so it wants to be 3 minus. So nitrogen is going to dominate and become 3 minus. Okay, so minus 3 oxidation state. Put the Roman numerals there. There's 2 of them, so 2 times minus 3 equals minus 6. And overall there's no charge, so the whole of the magnesiums together must equal plus 6 to cancel out the minus 6, because overall there's no charge in that molecule or ionic compound or whatever it is. Okay, so there's 3 magnesium atoms. So what do you times 3 by to make plus 6? Well, 2. So the oxidation state must be plus 2 for the overall thing to have no charge. 3 times plus 2 is plus 6. 2 times minus 3. 2 times minus 3 is minus 6. So the oxidation state of the magnesium there must be plus 2. Okay. So our next little section on the next little piece of video, because I think we're going to split them up so they're quicker to load, is going to be using these a little bit more and making up half equations and full equations from that.